Picture a single hour of sunlight. Not the gentle light that warms your skin, but the raw, unfiltered power beaming through the silent vacuum of space. In that 1 hour, there's enough energy hitting our planet to power all of human civilization. For an entire year. Think about that. We're swimming in an ocean of energy. But here's the catch. We're only dipping our toes in down here on Earth. Our solar panels are at the mercy of the atmosphere. They sleep at night. They get moody with clouds. They're practically useless in a rainstorm. So what if we could stop trying to catch the sunlight from the bottom of this cloudy, spinning pool? What if we could go to where the sunlight never ever stops? What if we could build a power plant, not on some tract of land, but in the endless day of Earth orbit? This is not a fantasy. It's a concrete nuts and bolts idea that's been sitting in the notebooks of scientists and dreamers for over half a century. It's called space-based solar power. And right now, for the first time in history, the pieces are falling into place to turn this sci-fi dream into our reality. We're talking about building the largest structures humanity has ever conceived. Floating 22,000 miles above our heads, harvesting the sun's power and beaming it safely down to Earth. It sounds impossible, maybe even a little crazy. But what if this is the key to unlocking clean, abundant, and constant energy for everyone on the planet? The race to build the first true power station in the sky is officially on. To understand why we'd even attempt something so audacious, we need to grasp the fundamental problem with energy here on the ground. It's all about intermittency. The sun sets, the wind stops blowing. Our planet has a rhythm, a cycle of day and night, seasons and storms. That's beautiful for life. But it's a massive headache for a civilization that needs the lights on 24/7. We've built this incredibly complex dance of power plants firing up natural gas peaker plants when demand spikes, hoping the wind is blowing when we need it to. Even with massive battery farms, storing enough energy to power a city through a long, calm winter night is a monumental, expensive challenge. But up there, in what's called geostationary orbit, it's a completely different story. A satellite parked at that altitude takes exactly 24 hours to orbit the Earth. That means it stays perfectly fixed over one spot on the planet. From up there, the Earth is a majestic, rotating marble, but the sun is a constant. It never sets. There's no atmosphere to dim its rays, no clouds, no weather of any kind. It's pure, undiluted solar energy, blazing away 99% of the time. The efficiency is mind-blowing. A solar panel in space can generate up to 10 times more power than the same panel on a cloudy day in Seattle. It does so consistently, predictably, around the clock. So, the idea is simple in concept. Build a gigantic solar farm in space, where the sun always shines, and find a way to send that power home. This is where the idea has always hit its biggest wall. How in the world do you transmit electricity across 22,000 miles of empty space? You don't send it down a wire, that's for sure. The answer is something we use every single day: microwaves. It's not the kind that heat up your leftovers, but a specific low-intensity frequency, or in newer designs, focused laser beams. Here's how it would work. Imagine our colossal satellite, which we'll call a solar power satellite. Its vast wings, spanning possibly miles, are covered not in heavy glass panels, but in lightweight, ultra-thin films of advanced solar cells. They soak up that constant sunlight and convert it to electricity. That electricity then feeds into a transmitter, a giant, but precise, phased array antenna. This antenna does something incredible, okay? It converts that raw electrical power into a coherent beam of microwave energy. This isn't a wild scattering blast. It's a tightly controlled focused beam, like the world's most powerful Wi-Fi signal pointed with the precision of a sniper's rifle. That beam is aimed with unbelievable accuracy at a receiving station on Earth. We're not talking about a giant dish in someone's backyard. This is a massive but relatively simple structure called a rectenna. It's a field of small dipolar antennas spread over a large area, maybe several square miles out in the desert or offshore. When the microwave beam hits this rectenna, the antennas convert the energy directly back into electricity, which is then fed into our existing power grid. Now, pause. I know what you're thinking. A microwave beam from space, pointed at Earth? That sounds like a James Bond villain's weapon. This is the single biggest question, and the most critical piece of the puzzle: safety. And here's the wild part: the science is overwhelmingly reassuring. The beam is designed to be what's called nanonizing. It's the same basic energy as your microwave oven, but spread over such a vast area at the receiving site that its intensity at the center would be less than the sunlight you're standing in right now. You could walk into the beam at the Rectenna site and feel nothing more than a slight warmth. Birds would fly through it safely. The beam's edge, its feather, would be so diffuse it would be harmless. The real trick, the absolute non-negotiable, is pointing accuracy. The system would have multiple redundant layers of control to ensure that beam never, ever wavers off its target. If it did, it would automatically shut down in a fraction of a second. It would be, by design, one of the safest and most reliable power systems ever conceived. For decades, this idea was a prisoner of the launch pad. The cost of blasting the thousands of tons of material needed to build a full-scale power satellite into orbit was simply astronomical. It made the whole proposition a non-starter. But something has changed, and changed dramatically. We are living through the dawn of a new space age driven by reusable rockets. Companies are now landing rocket boosters back on drone ships and reflying them, slashing the cost of getting anything to orbit by a factor of 10 or more. It's a revolution in access. Suddenly, the economics of building something massive in space aren't just theoretical. They're starting to pencil out. And it's not just cheaper rides. The technology for the satellites themselves is leaping forward. We're talking about solar cells that are no longer rigid, heavy slabs, but flexible. Printed films lighter than a piece of paper, with efficiencies climbing past 40%. We're talking about autonomous robotic systems that could assemble these gargantuan structures in orbit, like a cosmic erector set run by AI. We're talking about advances in phased array antennas and power beaming efficiency that are turning the transmission problem from a physics hurdle into an engineering challenge. So what does this look like in practice? Let's take a trip to the near future. It's 2040, over the Pacific Ocean, in a geostationary slot. The first operational solar power satellite, named Helios 1, is online. From Earth, it's invisible to the naked eye, just another star in the sky. But through a telescope, it would be the brightest human-made object in the heavens. Its vast arrays, made of a shimmering, gossamer-thin material, slowly rotate to forever face the sun. On the ground, in a remote stretch of the Nevada desert, sits the Rectenna field. It looks like a giant, sprawling chicken wire fence a few miles across. There's no smoke, no noise, no moving parts. It's just there. And flowing from it, into transmission lines that connect to the grid, is a steady, unwavering stream of 2 gigawatts of clean power. That's the output of 2 large nuclear power plants. But this one never needs refueling. It never produces waste. It just hums along, day and night, rain or shine, providing baseload power for millions of homes. The implications of that are hard to overstate. For nations with high energy demands, but limited land or inconsistent renewables, it's a game changer. Imagine a dense urban megacity or an island nation dependent on expensive imported diesel fuel. A single Rectenna site offshore or a nearby barren land could provide a huge portion of their constant power needs, freeing them from the volatility of global fuel markets and the limitations of their own geography. But here's where it gets really interesting. The applications go far beyond just plugging into the national grid. Think about disaster response. A hurricane wipes out the power infrastructure for an entire region, instead of waiting weeks to rebuild poles and wires. Emergency crews could deploy mobile, rapidly assembled Rectenna pads. Power satellite could redirect its beam to provide immediate, life-saving electricity to run hospitals, water pumps, and communications. Think about remote communities in the Arctic, where winter brings months of darkness. A space-based solar beam could provide them with constant power when their own ground solar is useless. And we can't stop at Earth. This technology is the key to unlocking everything else we want to do in space. Right now, any mission to the Moon or Mars has to carry all its energy with it, in the form of heavy, fragile solar panels or even nuclear batteries. But what if we could beam power to them? A lunar outpost in the depths of a 2-week lunar night could be kept alive by a power-beaming satellite in orbit around the Moon. It's self-fueled by sunlight. A fleet of robotic miners on the Moon could operate non-stop, powered from orbit. This transforms space from a place we visit with packed lunches to a place we can live and work sustainably. It becomes the ultimate power outlet for our ambitions in the solar system. Now, this path isn't without its cliffs and crevasses. Challenges are as vast as the structures themselves. Space is a brutal environment. Micrometeoroids, relentless solar radiation, and extreme temperature swings between sunlight and shadow will test these materials to their absolute limits. Building something that large in microgravity, with robots or spacewalkers, is a logistical puzzle we've never solved before. And then there's the cosmic scale coordination required. Who owns that slot in geostationary orbit? How do we keep the beams from different nations from interfering? How do we manage the traffic of construction shuttles and maintenance crews? This isn't just an engineering project. It's the birth of an entirely new, space-based industrial sector. The global race is heating up. The United States, through its Space Force and agencies like NASA and the Air Force Research Lab, is pouring serious research into power beaming experiments. If successfully tested, beaming power over a distance of 1 kilometer on Earth, a crucial proof of concept. China has explicitly stated its ambition to build a space-based solar power station, and they've earmarked it as a strategic national goal, with plans for a megawatt-scale test in low Earth orbit by 2030 and a gigawatt-scale commercial station by 2050. Japan and the United Kingdom have active government-backed research programs. Private companies are entering the fray, backed by visionary investors who see this not as a government megaproject, but as the future of energy infrastructure. We are standing at a crossroads. For over a century, our story of energy has been one of digging for coal, drilling for oil and gas, mining for uranium. It's been a story rooted in the dirt, with all the geopolitical tension and environmental cost that comes with it. Space-based solar power offers a different story. A story of building, not digging. A story of harvesting, not extracting. It's a story that begins not in the ground beneath our feet, but in the sky above our heads. It won't be easy. It will require a level of international cooperation and long-term thinking that is often in short supply. The first full-scale station will likely cost tens of billions of dollars. There will be setbacks, failures, and moments where it all seems too hard. But consider the payoff. A network of these stations could, in theory, meet the entire planet's electricity needs with zero carbon emissions. It could provide a foundation of energy abundance that lifts economies, stabilizes regions, and redefines our relationship with our planet. So look up tonight. See that steady, unchanging band of stars. Soon one of those pinpricks of light may not be a star at all. It may be a beacon of our own ingenuity. A silent, shimmering garden in the sky, harvesting the endless day. It's a promise of power that doesn't poison our air or warm our climate. It's a promise of a future where energy is no longer a scarce commodity to be fought over, but a plentiful resource beamed down from the heavens. The sunlight is there waiting just beyond the blue. The only question left is, do we have the courage to go and get it?